All right. Hey, good morning, everyone. I think we'll get started. It's been a minute after 11. Hey, welcome, everyone. Welcome. Good morning. I feel like a professor being in this university and standing in this room. So I hope I don't make you feel like, there's a lecture and I'm a professor. I'll try to do my best being interactive. So welcome to the first session of this year's Open Infra. So first of all about the title, yes, I ripped it off. After all, why not, right? The Fast and the Furious is never ending. I thought every movie was supposed to be the one last movie. It's never ending. They're just ripping it off with new actors, new generation of actors. So then why not? I'm going to use the same one and get myself an entry into Open Infra. So here I am. So just a little bit about myself. I'm Bharath. I'm from Mirantis. We're from the open source program office team. I lead the team. And so primarily what we do is focus on the upstream communities, the open source contributions, not just upstream communities, but not just that, but also focus on the internal teams inside Mirantis who work on projects that are related to the upstream communities. Right. So today I want to talk about Kubernetes and then the marriage between Kubernetes and OpenStack. Right. So yesterday in the keynote we saw. Resilience is one of the words that was really mentioned and highlighted, and the joining of OpenStack with the Linux Foundation has opened a lot of doors, right? And even before this official arrangement, we had this amazing compatibility between the both, and that's what I want to focus. But let's lay some foundation in the first place. So, why Kubernetes has become such a pivotal part of today's infrastructure ecosystem is because it provides a common centralized control plane across multiple providers, right? That's one of the main reasons why this particular ecosystem is succeeding, even though maybe some of the technologies are better, certain vendor-specific technologies, maybe they're better, but then the ecosystem is very nice because it can really plug into different cloud providers, whether it could be the hyperscalers or it could be the neoclouds, your edge and everything, right? So this is where Kubernetes really has that edge. And now, so when I was making this slide, I started off with the future of intelligence ops, but it's no more the future, is it? It's the today, it's the present that we're talking about, where AI has become the centerpiece of any and every discussion that we have. More and more in our private lives, more and more in our enterprise lives, right? Everywhere this is what we're talking about. And Kubernetes, coincidentally has a really nice platform and the basics for us to use that and utilize it for AI native workloads, right? So that being the center of our amazing wheel, it can work with all the cloud providers that I mentioned earlier, from the previous slide, for AI-specific workloads. This is a study that was done by McKinsey, where the AI infrastructure explosion has been studied in depth, and all of us know the crazy numbers that OpenAI has decided to invest in NVIDIA, recently with AMD as well, and NVIDIA itself being one of the giants in the space, right? So no matter what models are being developed, no matter what applications are being developed, I think we as infra folks need to understand that without an efficient, scalable AI infrastructure, none of that is going to be possible, right? So I think over the years, efficiency was not really, one of the keys. Having the infrastructure was the most important factor, and that's why crazy amount of money was being poured in. But as the time passes on now, as we move on, I think the efficiency, availability, scalability, and one of the more important things we'll talk about, sovereignty, becomes all the more important, right? So it says that in order to accommodate the current needs and the growth of the industry, we need to grow 33% year on year until 2030. And the second important pivotal thing that I got out of the report was about the sovereign providers. So while the hyperscalers are extremely available and easy to get, they are also expensive. And for somebody who is just developing apps or even a small to medium scale business, that's not really practical all the time, right? So a typical cost for 1 hour for NVIDIA DGX H100 was marked at $98 per hour versus $34 per hour in neoclouds, which are basically the infra cloud providers who are not the hyperscalers, right? Now, with this, I want to highlight the challenges with AI infrastructure. Hyperscalers, yes, like I said, it's available, but for the rest of us, for the businesses that are consuming it, hyperscalers have come with a lot of challenges. So one is the GPU availability. I think this is improving day by day, but it's still not a solved problem, right? If you are a serious business wanting thousands of GPUs, you still got to get on a wait list and wait for the GPUs. This was even more evident a couple of months ago, but now again things are slowly changing. But it's never a sure shot confirmed thing, right? Because regulatory changes are never under our control. And then you have the vendor lock-in as well. So this has become a serious concern and a more important thing nowadays than before, that the control of infrastructure being in the hands of a few hyperscalers is always a thing that is at risk. And yesterday this point was mentioned as well in the keynote, that we don't want to be heavily reliant on 1 or 2 companies or 1 or 2 countries, right? So that becomes all the more important. And then expensive, like we already showed in the McKinsey study, right? So the more you want to scale, and the funny thing is, once you get into the business and once you start training your models or serving AI workloads, then you get to a point where it's hard to go back. So you can't really go back once you've committed to it. And so what happens is you have to commit to the particular vendor, and then that bill keeps going up and up and up, right? That becomes a really problematic scenario. And then there's data gravity and compliance. I think, this is something that we all understand today. More and more data that doesn't have to go public can't be utilized for AI training, can't be utilized for serving models, and can't be utilized for improving our models, right? So for that, we need on-prem infrastructure. And that's the core of what I want to focus on. OpenStack that provides on-prem infrastructure, how can we utilize that in order to do all the things that we're talking about, right? Another thing that becomes very important is the latency and then the egress costs. So I know it's extremely easy to just click a button and then get load balances in one specific region, and if you don't want, you can skip the region and put it across into some other region so that we can improve the latency. But all these come with a cost, right? Both in terms of economic cost, but also in terms of regulatory costs. So just because we have the option to spin up VMs and regions and then set up egresses, doesn't mean that always we can, because of the regulatory norms, and that's more true in Europe than anywhere else in the world, where data cannot leave the European Union, right? So this is an agreed upon thing from ages, and it's not going to be any different with AI. In fact, it's going to be more important, and it's going to they're going to stress on this point more and more than traditional applications, where we have to be extremely careful to meet the regulatory compliance and the loss of storing the data, right? And this is where we are. So I've talked about problems a lot, right? Now, what about the solutions? So we have a bunch of solutions, but one of the solutions that is really accepted, tried, and tested for years is OpenStack and Kubernetes, right? So OpenStack has been proved very successful in really different kinds of businesses. Whether it's, yesterday we saw one of the amazing presentations which was about weather forecasting, right? I can't even begin to process the numbers that was put up on the slides, like how many terabytes, how many zettabytes of data, right? Every day we're getting like loads of data, and I think that's a very good analogy for AI workloads as well, because the more data we have, the better the models are, and we have a lot of data. right? So OpenStack has already been proven to work there very well. And talk about the other extreme end, even for edge deployments, people have been using OpenStack, right? So we have Raspberry Pi set up, and then made to push data onto the cloud, and then the controllers that are sitting on OpenStack processing all this data in real time, giving us near real time results, right? And we also know of car companies which are using this. It can't get more real time than that, right? And medical hospitals and medical companies using this, where we are monitoring, we have thousands and thousands of sensors, and all the sensors data is going into a small device, and then from the small device onto the cloud, or even an edge controller sitting on the edge, not even the cloud, where a lot of processing is being done. So my point is, for all sort of scenarios from extreme edge to huge hyperscaler based sized data centers, OpenStack has proved to be reliable, right? And then we have the second one, which is Kubernetes, right? So again, like I said earlier, it's not always the best technology that always wins. Maybe there's better technology, but the people, the ecosystem, the acceptance is what matters so much in this industry, and that's what we see for Kubernetes. Like, if you guys have been to a Kubernetes conference lately, the number of observability companies are crazy, right? Like, the booths are just filled with observability companies. Why? Because there's a need, and because it's so open source and free, you can just come up with one feature and build a whole company around it. That's the freedom that Kubernetes gives. Or you can literally use a package in production which is developed by one guy, maintained by him, and completely run by him, right? We have both the ends. That's the flexibility that Kubernetes provides as well. And I've put in this word called cluster intelligence. So I mean, it's such a vague word and a vague topic to talk about, right? But what does cluster intelligence really mean? The way we integrate AI can be done at various levels. So if we keep aside the end user applications for a second and focus on the infrastructure, where and how can we integrate AI, right? That's what I think the entire industry is moving towards now, trying to solve this problem or trying to provide parts of solutions for this, right? We have Ansible, and then there's Ansible AI. We have Terraform, and then we have Terraform AI. We have kubectl, and then we have kubectl AI. kubectl AI was one of the fastest projects to get into CNCF Sandbox. Why? Because they integrated the AI in a very proper way that's very useful for a platform engineer or a DevOps engineer to use and utilize and actually make use of the features of AI, right? And that's why I put the word cluster intelligence, where it's a combination of multiple things that goes into this platform, which work together to provide you a good result that's making our lives better, right? And this is where the combination of these two things gives us our own AI cloud, right? I think in a couple of slides I have the demo. I'm going to show you guys by using one of the clouds where I have OpenStack that's available for me, public instances from OVH Cloud. In fact, they were really generous to donate the infrastructure for this session once I reached out to them. So yeah, shout out to them. And then Kubernetes, of course, right? But which part of Kubernetes? And that's where I want to introduce Cordant, right? So Cordant is based on Cluster API. For those of you who don't know Cluster API, it's basically a Kubernetes project, a project that is under the Kubernetes 6, which automates Kubernetes infrastructure provision, right? So a bunch of people got together and decided that this is the standard way that we will use in order to provision Kubernetes clusters, right? And all the cloud providers like Kappa for AWS, KapZ for Azure, Kappa for OpenStack, and so on, right? All of them agreed that, yeah, this is the standard way to do things, and each of them have their own implementation of the controllers in order to work with this, right? So what Cordant does is essentially like three things: cluster management, state management, and observability and FinOps. So let me start with the last thing, because it's like pretty straightforward. Any platform that is built without observability, without eyes and ears, is useless. So that's why we're using most of the open source solutions, which I'll show later, and we are baking that right into the platform. And then these two, corresponding things, mirror things. Cluster management is to take care of the cluster provisioning, which is powered by Cluster API. State management is the component that's responsible for service deployment. So that's basically the day 2 of services, right? So we have the cluster. It's amazing. It's all provisioned across OpenStack. But then what next after that? So that's what is taken care of by state management. And for this, we're using another open source project called as SvelteOS or SvelteOS, right? And yeah, like I said, the underlying layer will always remain your infrastructure of choice. And since we're talking about like OpenStack and private clouds, on-prem clouds, that's where this is going to be. Right? Yeah, I don't want to jump too much into this, but essentially, yes, this is the complete Cordant stack, so to say. We can even call this as the IDP. If you just put one more application on top, that becomes your IDP, internal developer platform, right? But Cordant itself is not directly into providing IDPs. It's more enabling the platform engineering team to provision clusters across the clouds. And on top of that, you can definitely build your IDP. And today, we're going to be focusing on these two boxes right here, which is the cluster management and the state management. All right. So essentially, I'm going to show you the YAML right after this, but just to give you a heads up what it's going to look like. We will deal with one centralized YAML file, which is cluster deployment, and we define our cluster configuration and services configuration all in this one single YAML file. I know you're all thinking like, again, more YAML. It's true, like we can never live without YAML, but we aim to simplify YAML, let's put it that way, right? So instead of yamming hundreds of YAML files across your GitOps repository, we plan to centralize it into one particular YAML file. We call it the cluster deployment, similar to deployment of Kubernetes, but it's for a cluster, right? So we have like two controllers, Cordant controller and SvelteOS controller, working together for the cluster deployment part and then the service deployment part, right? Just to shout out the Cordant catalog. This is basically the services part. Again, like I said, this is completely open source. So what happens is all the applications you can find it at catalog.cordant.io. So for example, Istio is a common service that we want to deploy. Cert Manager is a common service that we want to deploy across clusters, right? So you go to catalog.cordant.io and then see the cluster, you install it. That's it. We also support applications that are private to you, that are not public, right? You can still reference it without being available publicly. You can still reference it in your Helm repository. Okay, so let's see. Live demo right now. Alright. So in the interest of time, obviously just before, last night I provisioned the clusters because this is like a 30-minute session. So I'm going to show you the cluster deployment, and then I'm going to show you the things that exist, and we can access the cluster directly and see what's happening. Right? So far, what I talked about AI in the beginning, right? Let's do a catch of this. So this is how we essentially, reference the cluster deployment. We have a template that tells Cordant which particular cloud provider to use, and then we have the credentials to be configured to talk to the cloud. And then this entire block is just the infrastructure specific configuration. So this changes for each provider. Since we're using OpenStack, this is how it would look like, right? So we have the control plane definitions, we have the worker definitions, and then we have the anti-refs, and so on, right? Pretty standard configurations. And then the day 2, what I mentioned is the service spec, right? So if any of you have tried configuring all this by hand, you all know that how painful it is to do it step by step. But this is what I'm trying to explain, that by just mentioning the service that you want to deploy in your cluster deployment, as soon as the cluster is provisioned, Cordant will read this YAML configuration and actually deploy the NVIDIA GPU, right? And I want to show you the cluster templates and service templates. This is how it will be, right? So, like I said, it provides like all the major providers, but today we're going to focus on the OpenStack hosted and standalone. And in the earlier cluster deployment that you saw, I had referenced the standalone CPU, right? And then you have the service templates. So for now on this cluster, I only have the GPU operator installed. But if you want to install, so this is how easy it is. So you can go to catalog.cordant.io and then try to find the service that you want, and then just do help pre-install, the name of the operator, the name of the application, and then the URL. That's it, right? And then it'll come up here, and then you can reference it in your cluster, right? So I had already applied this. So let's check this out. There you go. We have the cluster deployment ready. And just to get a little bit more technical, I can show you the cluster API objects, right? So we have the cluster, and then we have the OpenStack cluster, and then we have the machines and OpenStack machines, right? So what these are basically VMs that correspond to, these are like the control planes that correspond to the VMs on your cloud, right? So here I have accessed the kubeconfig of the particular Kubernetes cluster, and let's do that. Here we go. This is the cluster that we've provisioned. It's accessible here, and let us also check out the GPU operator pods, right? Yeah. So essentially, the NVIDIA GPU operator does this. That it goes and installs a bunch of requirements, dependencies, plugins, drivers, and all these things. And one of the most important things it installs is this container toolkit as well, which essentially tells your underlying Kubernetes cluster that this cluster has GPU attached to it and you can use it, right? And let's see the nodes, and then let's do a describe node on the worker node, because I'd only chosen a GPU cluster for the worker. For the control plane, I'm using a CPU only machine. And over here, to do that, awesome, right? So, sort of proof that the NVIDIA operator did its job is that on my node, I have this annotation that NVIDIA.com/GPU that essentially tells the cluster that you can actually schedule AI workloads on this particular cluster, right? It's as simple as that. And let's say that we want to extend this or update anything, right? It's just a matter of changing the configuration over here. So for now, obviously, I've just used like one control plane and one worker node. But if you want to increase it and make it 3 and 3, the way it's in standard deployment, that's it. We just have to change this, right? And similarly, for all the other parameters as well, it'll be like one central place to update the configurations. All right. Getting back, just want to show the catalog ones. Yep. So when we started, it was about 20, 25 applications, and then we grew, and then I think it's about 70 plus applications right now. People have been contributing, to it. And one of the things that I want to show you in this as an example is the FinOps agent that one of my colleagues built, which is an example of a private application that you might have, right? So as you can see, most of the things over here are standard applications like GitLab, Grafana, Headlamp, and so on, right? But this is an example of an application that my colleague built, which he just packaged it as a Helm chart, and that's it. So if you don't want to upload it here, that's fine too. Like I said, you can put it in your own Helm repository and then reference that Helm repository. That's it. But if you think it's in public application that will be helpful for the community as well, which is what this one is, So he just put it up here, and rest of them can utilize this as well, right? So there's another example. Oh yeah, and just to close the loop here, this one I want to show you the corresponding things here. 1 second. There's the OVH cloud. Right, and then we have the instances and all the resources. There. So the Kubernetes cluster that we are seeing on our terminal essentially maps to the OpenStack that we have right here. All right, I think I'll just wrap it up in like a couple of minutes. So just to summarize, this sort of marks the entire OpenStack ecosystem that Cordant uses. On the left side, we have the cluster management with the cluster API and all the corresponding components, state management in the center with SvelteOS and Argo Flux and all that, and then observability and FinOps with Prometheus, Grafana, OpenCost, OpenTelemetry, and so on, right? And just a quick word about the KServe on the left side, right? So KServe is basically a Kubernetes distro, much like K3s, Kine, and all these, right? It's a Kubernetes distro. Again, this is yet another open source project, and KServe is extremely lightweight as well compared to the other distros. So this is the underlying Kubernetes distro that's used in Cordant as well, right? Yeah, thank you so much. Let's definitely connect outside. We have a booth as well ongoing. If you have more questions, more than welcome to answer them, talk about it. And then check out cordant.io, KServe's project, and then of course opendev.org as well. And you can scan this to connect with me. Thank you. I think we have a couple of minutes. Do you guys have any questions?
Do you have like a seed cluster to actually manage the state of the clusters you deploy yourselves, or is it just local state?
Yeah, so for this particular one I use Kind, but essentially yes, you're right. There will be a management cluster or the mothership cluster, which has the cluster deployments of all the clusters.
Oh.
So the observability part, what I mentioned, that gets deployed on the mothership cluster. So you have like one central pane across your multiple clouds. So this is again, I think, one of the things that was lacking in the industry, where like AWS has their own portal, great. Azure has their own, OpenStack has their own, right? But what about a centralized view to manage all your clusters, your observability, your costs, right? End to end of it in a centralized, place. So yeah, the mothership cluster is where Cordant is installed, and then the controllers of Cordant are on that, and then multiple clusters. All right, thanks again. Yeah, I've been more focused on
Ja, genau. Man sitzt sich ja da.
It's picking up on my laptop. Oh, there you go. Okay, let's get started. Okay, we'll get started. So hello everyone. This presentation is called Talking with Your Infrastructure. It's about AI agents and how to sort of work with OpenStack, Kubernetes, or any infrastructure with AI, which is fairly a high-level presentation. On the topic, the agenda today is to give a quick introduction, talk a little bit about LLMs and agents. We'll go on to how to build a sort of an agent or a chatbot using LLM with RAG, fine-tuning, etc. Do a quick demo on the things that we will talk about, and then if we have time, we'll do some Q&A. Okay,
something about myself. My name is Suloshan Acharya. I work at Rackspace. I've been at Rackspace for quite a long time now. Rackspace now is getting back to, with Prometheus, getting back to doing a lot of OpenStack again. And some of the stuff in this demo, we're using H100 GPUs in Rackspace Spot. So if you're into those kind of stuff, go check it out. Now, AI has been sort of a, we're kind of at an inflection point with AI. Because it's not just about optimizing how to do stuff, optimizing your workflows, or even not just about provisioning AI, but it's more about a fundamental shift in how AI can shift the focus from just doing manual provisioning of workflows into sort of like an automated stuff. And so it's a driving force now, and then we're experimenting a lot of AI-driven operations, and this came about at Rackspace, where I work on a lot of OpenStack-related stuff, but I also work on this platform called Pixabay, where it's a platform that sort of brings in OpenStack, Kubernetes, and VMware, all these clouds into one place where you can deploy AI, but also sort of be in a place to experiment with your LLMs and chatbots, right? And so this whole idea of doing AI bots or AI agents for managing your infrastructure came about for purpose of having a unified platform and then allowing them to work with it to be deployed through AI. And so basically the vision is, because I'm a big fan of Iron Man, and so when Iron Man talks to Jarvis AI, I always wondered if there was ever a possibility to do something like that. And recently that became more and more clear that there is, it is going into that direction, right? So voice to text is established technology now, and going into GPTs and having AI now, with LLMs having text into action is becoming more and more clear, like a Jarvis-like AI would at some point be possible. And so the aim was to build something like that. So imagine having an infrastructure like your OpenStack cluster or your Kubernetes cluster, and rather than typing commands or having to know commands, you just question it, saying, hey, can you give me something? Can you build an instance? Can you deploy a workload? Can you provision my Kubernetes workloads? And having that done. Right, and that was the vision, that still is the vision, to build an infrastructure like that. And so in building that, you have to be context aware, it has to be data driven, but how do you do that? So, just having an LLM, having a wrapper around LLM, will that work? What is it that we need to have a complete platform that things like Jarvis, for example. And that leads us into having AI agents with LLMs as the cognitive layer for this work, and this is where we're going. And so, just to recap, what is an LLM? A large language model is a sophisticated piece of software and its main aim is it's like a prediction engine. So its main aim is to predict the next word or tokens in a sequence of words, and that's what an LLM is. Its completion capabilities comes from having it trained on a large volume of data, terabytes, petabytes of data. Some of the larger LLMs are very, very huge, right? The amount of data being trained on, and then they have the important thing is they have a context window, which is sort of like their short-term memory, which is how they behave. The context window is recently been growing and growing, which is awesome. And then they might give you an impression of reasoning, but obviously they're not reasoning, they're just predicting next words. So that's very important. So for engineers, OpenStack providers, users, it's important to know that this is not a source of truth. So if we're using an AI agent type stuff to troubleshoot something, you have to understand that whatever an element says might be completely bogus, right? So that's something that we need to keep in mind. What is it good for? It's an excellent excellent way to recognize patterns, and so you can fine tune it, you can teach it to predict how something would go if you ask it a question. But LLM by itself is obviously not enough. I'll actually go to a slide. By itself is not enough. So if you write a wraparound LLM, obviously because it has no context of what you're doing. For example, if you're an OpenStack operator and you're asking a question about, let's say, about something that's broken in the infrastructure, like a build fail, and you ask it a question, it has no idea because it's not trained on that data. It will just give you some generic data that's been trained on. So we need AI agents. And what are agents? Agents are, again, a piece of software. They're sort of like a bunch of autonomous software that take input, interface with your infrastructure, whether it's an API, whether it's documents, whether it's a pre-written something. It will take that, it will reason it with the context, and then it will provide that context back to an LLM to then take another action. So I'm sure we've heard of these AI agent swarms where you put the multiple agents together and then they will troubleshoot your stuff. This is sort of where the way that it works is by one LLM taking a command from, let's say, user input, and then providing that command back to, say, if you're asking a question about OpenStack, it will pass it on to an OpenStack agent, which will then go query your OpenStack API, come back with an answer, go back to the LLM, and so on. So it works on reasoning, action, and then the feedback then is to go back to the LLM and then feedback back to the user. So LLMs with AI agent is sort of the cognitive layer of where having a Jarvis-like system is going. LLM brings the reasoning, the context understanding, and then the AI agent, sort of the intelligence and action, from your infrastructure into it. So agents then bring sort of like a grounding in terms of data to your application. They provide memory and state management. So if you're asking it a question about build failure, it has to go fetch multiple things. It might have to talk to your logs. It might have to query your APIs, so on and so forth, and then bundle them together to provide that sort of management layer to provide back to the LLM. And so the decision and policy enforcement can happen on this layer. And again, you can talk to your tools and APIs, right? And over time, this sort of cognitive layer sort of evolves into a more reactive, autonomous AI bot. Why do we want LLM agents right now? And there are multiple reasons. LLMs have matured to a state where, just for example, larger models like GPT-4, some of the other are so DeepSeek models are good enough to just answer your questions because they've been trained on such large volumes of data. So even if you ask a question about, okay, what is the right way to fix an issue in OpenStack, I'm sure a lot of us have done that. I do it regularly nowadays. It comes back with the right answer most of the time, right? And so it's good enough that we can use that now as the base of our next level AI agent platform. And then we have lots of telemetry data nowadays, so many APIs, so many monitoring and logging and infrastructure, which all provide data through APIs. And so that's a great way to sort of feed that back into your agent, and then you can make a more sort of decision that's more relevant. And then OpenStack, Kubernetes, they're more hybrid. There's so many, within a cluster, you might have multiple things, you might have multiple clusters, and then just managing that will become difficult. So having a autonomous sort of agent to do that would be right at this point in time. Right? So, and again, move away from manual operations into sort of intent-driven ops. Again, so Iron Man like Jarvis. Two ways to look at this. So if you're here, you're either an operator, running OpenStack day to day, or you're a user using OpenStack. So you're either spinning up a virtual machine, or you're looking at the backend and saying, this is how it works. And so what we're trying to do is we're trying to build an SRE AI agent or an SRE AI chatbot for backend users, for engineers. If you're a user, you might not know. You could go click on the UI, but you still need to understand how everything works. Let's say you spin up a VM, you have to create a network, you have to create a router, create the floating. You need to understand all that. So for a user who is not very familiar with cloud technologies or OpenStack, you would want to provide a personal cloud AI engineer, which you just say, hey, build me a server, and it goes and does that. And so, like I said, agents required, because just having an LLM wrapper is not enough, since it doesn't have the context. You ask it to do something, it only knows about the data that it's been trained on, so it's going to come back with something that's maybe not relevant for you most of the time. And so when we were building this, we tried that, and we said, okay, that doesn't work, let's garbage. We'll do something else. The second pass was using LLM with simple function calls, and we'll talk about function calls in a second. So function call is when you say, hey, build me a, or what is the status of my cluster? It goes on, queries your API through a function, and then comes back and says this. It works, but it's still error prone, because your LLM needs to really understand all the functions. And, if you have a large list of functions, it's going to not exactly hallucinate, but it will call a wrong function for a call that it should not be making. And so third, we tried function call with RAG, so give it a bit of context. So the first call would be, if I ask you a question about instances, look at my vector database, fetch me some context that tells you then to go and call a function. That is still, but RAG is sort of like a beast on itself. So if you don't have the right quality of data in, you don't have the right sort of structure in your documents, then again it comes back with wrong answers, right? And so the final pass, which is where we're at right now, is having LLM, which is fine-tuned for your purpose. So in this case, we're fine-tuning it on OpenStack and Kubernetes-based stuff. So for example, when I tell it to, what's the status of my instance, it's already been fine-tuned to know that it needs to call a function, and that function is called X, right? So fine-tuning it makes it a bit more focused on your job at hand. So what we did was we fine-tuned GPT-4. We also fine-tuned Quen, which has excellent function calling features. And so these models were able to, once you fine-tune it, were able to correctly then identify, context from your documents with your RAG, and then provide that context back to your agent. So that worked. I mean, there's still a long way to go, but that's sort of like a thing that seems to work so far. And so the strategy then, if you're doing something like this, is model selection is obviously very important. The model that you select, whether it's GPT-4, whatever it is, must do two things. One, it must call functions. It must be very good at calling functions. There are many models which are not very good at calling functions. We were working a lot with, for example, Llama, and it does call functions, but only with like a very large, let's say a Llama, like a 40 billion parameters model, right? Which is kind of hard if you're just running like two GPUs at H100. So in order to make that happen, you need smaller models that you can run within a GPU, 2 GPUs, and still be very effective at calling models. So your model selection is quite important. Second, fine-tuning model for tool calling. So supervised fine-tuning, which is what we did with GPT-4, with Quen, Llama as well, to some extent. There is a lot of literature around this. I mean, that would be like multiple presentations just to go on fine-tuning. But I'll leave it at that. And then integration of RAG, retrieval augmented generation, which is providing your specific domain knowledge to your AI, to your large language model. So select the right sort of vector database. Plenty out there. Have the right document in the right format, and then your RAG then will provide like a proper context to your AI. And finally, the agent AI integration, which combines all of these through agents. So your agent will now do RAG calling, will also query your APIs, and so on. Really high level sort of view is, you have agents, a handover agent, which is how so your LLM, your user input goes into your handover agent. Your handover agent, depending on whatever you're calling. So if you're asking it about your your infrastructure in Kubernetes, it will hand over that call over to the Kubernetes agent or OpenStack, or if there is a human in the loop sort of thing, then through chatbot dashboard, etc. That happens. Obviously, queries, events, and logs. There could be many more here, right? But in our case, this is how we're looking at it. That's the platform we're doing this. It's just a quick view on how that looks like. But we'll do a live demo in a second here. Couple of things down here. There's like a front end working, which is the sort of the interface into which you will talk to your cloud app. The second thing that's running is an OpenStack agent. You'll see that the main handover agent running there as well. Then the Kubernetes agent, and then the backend that provides sort of everything there. There's other stuff running there, but you just want to focus on those 4 agents plus the backend and front end that's running there. Right? And so the OpenStack AI agent is what we'll focus on. This again, this has the same thing applies for Kubernetes, same thing applies for VMware, whatever you have. But this is sort of like we will focus on the OpenStack part for now. Actually, I'm gonna go straight to this part, which is, so as I said before, when we were writing the agent, it needed to have one function calling. And so this is where we define. I have a whole bunch more down there, but this is how we define for the agent to know what to call when something happens. So these are the available tools for it. So when I ask for, let's say, on OpenStack, when I say, okay, give me what are my OpenStack regions that's within the platform, it needs to know what to call. So when I'm either fine tuning it or when I'm doing a function call, I've defined my functions for the agent itself to know. Second, the function call definition itself. So when the LLM or the agent or the LLM needs to know when it calls the function, what are the sort of the parameters that goes into the function. So if you say creating an instance, it needs to know that I need to call create instance from back there somewhere. So create OpenStack instance, and it needs to know that it needs to call a function, but it also needs to know what parameters to pass into those functions. So right now I said, the very last line, I'm saying just the name and the region is required, everything else I can default. So you could easily just say like build me an instance in region X, and then as long as you configure that region X of OpenStack into your system, it's going to go and build that for you. And then finally, the function itself is not very important. Just a basic Python function that eventually will just call a OpenStack API to create your instance, right, or whatever you have. And so the flow then is for your OpenStack API, or sorry, your OpenStack agent. So when you say, what's the status of instance X, the handover agent knows that you're calling OpenStack, it passes that to the OpenStack agent. Given the context, it knows what function to call and what parameters to pass, and then it calls that and then passes that answer back to you, right? So that's basically the flow of things. And here on the back end, so this is how it looks like. When I say, using flavor, blah, image, blah, keep here, etc., create me a new instance in this region. And so the first thing is it get that sort of the context get passed into your handover agent. The handover agent again it knows that it needs to call the OpenStack agent which calls the LLM. So it passes the same thing back to that OpenStack agent. The OpenStack agent then calls LLM, which realizes that you need to do a function call, and so it calls the create OpenStack instance with the provided arguments. The OpenStack agent comes back to OpenStack agent, which does a post call to your OpenStack API. Once that's done, it sends the whole context back to your LLM again. When that's done, you get an answer back. And so that's the flow of how this agent workflow works. Right? And this works for spinning up an instance, works for troubleshooting something, works for doing any automated any sort of work both on OpenStack and on Kubernetes. That's just an example. We'll do a live one right in a sec. Missing there, I'm probably asking it. Oh, that's the build command that I was asking it to. It said build an instance, and it did a build and then came back with that. And so we'll do a live demo in a minute here. And then just so going back to talking with your infrastructure. Once you have this going, I'm choosing, just in the demo as well, I'll choose the easier, simpler sort of commands just so that the demo gods are happy with them. There are more complicated ones where you say, go troubleshoot my build failure. That takes time. They'll go in, it'll fetch different things from different places, and then figure out the reason why this build is failing. It takes a few minutes, so we'll skip that. But easier ones, things like like they can do right away. How many regions do I have configured in my system, etc. And those will, again, we'll do in a second. Those will work fairly quickly. And again, this is the sort of like the example of talking with your infrastructure, right? Now we come. So that's great. Those are function calling, agent calling function to do something. We have, as operators, we've all seen cases where we have OpenStack infrastructure, Kubernetes infrastructure laid out, and then we have problems. And so we need to provide, a simple way to figure out how these problems can be solved. And obviously, everyone has their knowledge base, they have their sort of, in-house knowledge base, etc. And you might have, engineers with shift admins, etc., who need to know this, and how do you pass that along? If you have RAG configured in a way that you ingest all your knowledge base into your RAG, this becomes really easy, and we'll see that in a second. Because retrieval augmented generation, it allows you to retrieve, sort of depending on your query, retrieve the data that you would require to figure out a problem. It will augment that into the context for the large language model to process, and then that would generate the right sort of response for you, right? So let's take a look at this. We'll again do this in a second here. This is one example. How do I deploy? Okay, this one's I'm just asking, how do I deploy Magnum with Cappy? And well, if you don't know how you deploy Magnum with Cappy, you're going to go on the internet, start searching for stuff. If there is a curated documentation, this comes from, again, this is documentation from Rackspace Cloud right now. All that Rackspace Cloud documentation is fed into the system. So when you ask it questions, as long as your vector database has it properly embedded, it's going to come back with a right answer, and that answer is a sort of verified answer from your documentation. Right? So that's one way to do this. Before we go into demo, kind of running on time as well. Sounds awesome, sounds good, but there are integration challenges, especially on security and trust. And so agents are operating sort of your instructions on some region, some production. If you're running this on, how do you make sure that it doesn't disrupt production stuff? How do you make sure that it's doing the right thing? So there is a lot of and who's doing what? How do you sort of make sure that the right person is doing the right things, etc. So there's trust boundaries. Obviously the data silos. So we need to fetch data logs, but logs have a lot of stuff, right? So does everybody have access to that level of details? Same for metrics and so on. And how do you make sure that there's multi-tenancy within this? So if you're a user, you're asking it a question about your infrastructure. How do you make sure that another user doesn't do the same, or doesn't get the same answer? Can do the same. Again, integration with APIs and auth, scalability. How do you make sure that this agentic platform works on multiple regions, multiple clusters, and so on? So there are lots of integration challenges. Like I said, mostly on trust and safety. So because we're working directly with mission critical infrastructure as backend engineers, so we need to make sure that we take care of that. I'm going to rush a little bit because we're running out of time. one thing I do want to mention is, when we're doing agents, we need to make sure that there is some policy guardrails put on, so that, agents, it operates within a strict pre-approved boundaries. And so when you're doing this, you say that, okay, level A, B, C, D, and this is where, whoever asking the question has access to this level of details, etc. And then that guardrails act as a, sort of your pre-auth with validation pipelines to make sure that you're giving out the right answer. So you might ask it a question. Let's say you have done this and you provide this to your, with your clients or your support or whatever you have, and then they ask a question and the LLM gives a wrong answer. Now we need to make sure that validation, that answers are right? Access control, safety, etc. Key takeaways: AI agents, AI in general will help us, build better product for our customers, and will help us troubleshoot stuff as backend engineers, etc. In order to do that, data unification is important. You need to have like a very effective way to get that data back. Trust and safety that we just talked about, and finally, the future of SRE is cognitive and collaborative, and let's try to build a Jarvis-like system. So we'll do a quick demo. Okay, and so let's go back here. So this is sort of the platform that So if we go back here, we have OpenStack regions, etc. defined right here. So I have my OpenStack here and my Kubernetes cluster here. And so if we go into the chat and say, what are my OpenStack regions? Okay, so we have those two. Let's see if I have any instances here. Okay, I'm going to copy that. And it says, give me details on instance flex. Okay, and that's basically the read. And so we can do something a bit more. So I have a Kubernetes cluster as well. So I can say something like, look at KServe and tell me the status of my cluster. So I have completely wrong example. So I have a Kubernetes cluster configured here, and then it's saying, looking at the events, I have some DNS config formation errors, etc. So it tells you, what's unhealthy, etc. So that's another one. So let's build an instance just to be. I have the command handy here, so I'm just going to copy it. So using flavor, this is again the same from the example. Using flavor, can you build me an instance? And if we go back to OpenStack, I only have my instance here, just call that. Refresh that. There you go. There's a build happening. That was what this came back with. And so again, I'm picking easy examples where you can do the same with why did my build of instance X failed, or what happened to network disk, etc. And it will go. That will take a long time, but it will fetch. It will go and fetch information from your logs and from your APIs, etc. And then come back with an answer. We're really running on time, so that's basically what we're trying to build. And as we build this, make it more and more sophisticated, be able to do sort of more autonomous action. So there is pipelines where if an error happens, actually the last one that I want to show with RAG is, so we have infrastructure with lots of stuff happening. I'm just picking this as an example. And so a MariaDB replication is broken. I click on this. I have a very specific instruction for it to do similarity search from my database for my issue. And hopefully it came back with the right, yeah, it did. So it says this is how you fix MariaDB replication. This is right from your knowledge base, and so it becomes really easy. And so you can do this basically for every single problem that you might have in your infrastructure. So in this case, it's MariaDB broken, could be anything else. And so I'm sure we all have our own sort of knowledge base to work on, and then this can help. We're on time, so thank you very much. Happy to take questions or